And it looks like the microphone is working good. So first, as usual, please tell me that you're here. Boop. And then let us begin. So we're going to finish up these slides and some others today. We have a lot of work to do. So let us pick up where we left off. We were talking about different logical operations. We were talking about circuits that could use those operations to perform tasks. And now I want to talk about binary. Okay? How to think in it, how to use it, how to convert between these number systems, these bases. It's going to be super fun. So I'm going to hopefully answer this question for you. Like, oh, okay, I've heard about ones and zeros. Maybe I've thrown that term around in this class. What does that mean in terms of all of these logical operations and how a computer works? And now is the time to learn about all this stuff. So 1 is true as far as the computer is concerned. Okay, and 0 is false. That's it. High voltage is true, low voltage is false. And every single piece of our computer, except for a little tiny bit, is made up entirely of those logic gates that we were talking about last time that were performing those logical operations that we also talked about last time. Okay? That's it. That's how computers work. It's really weird, but it all comes together in the end. And yeah, everything, as you know, stored on a computer, right? In your hard drive, on your flash drive, wherever. All that stuff is just a bunch of ones and zeros in a very special way to encode all the stuff that we want, like this PowerPoint, okay? It's really cool. So let me talk to you about binary. Let's learn how to convert between it. So let's start with talking about the number system that we know and love called base 10, okay? That's the number system we write our numbers in as humans that we like to use. It's called decimal, right? That's another word for it, decimal. Our decimal number system, okay? And we call it base 10 because there are 10 digits for us to work with in decimal, right? We have 0, 1, all the way to 9. That's 10 digits total, okay? 10 digits. 0 counts as a digit, so that does make 10. Yeah, digits. And because we only have 10 digits, once we have 9 and we want to add one more, we have to introduce a new place, right? We have to make it 10. We have to introduce the tens place because we didn't have any more digits to work with to keep a single digit number. Okay, that's it. That's decimal in a nutshell. Binary, though, is base 2. Okay, so following this pattern, there are only 2 digits that you get to work with in binary, right? Just like for base 10, you had 10 digits to work with. So in binary, you get 0 and 1 to work with. That's all you get. And so if you are working with 1 and you want to add 1 to 1 in binary, you don't have any more digits in the 1's place. So 2, as far as binary is concerned, is 1, 0. Okay? And this is going to get very confusing because this looks like 10, this looks like 10, but these are completely different numbers. This is R10, this is 2, or 2. So the way that I'm going to differentiate between numbers written in different bases is with a subscript. So here is the decimal number 10. I'm just going to write the base down like that. So this is 123 base 10, okay? And this is 2 base 2, okay? 1, 0 base 2 is decimal 2. Does that make sense? I'm going to write these numbers. Okay. Hopefully that's not too bad. And yeah, people got fancy. They didn't like to say binary digit in a binary number. So instead they call it a bit. They took this B and this IT. And so a bit is just a digit inside of a binary number. And a byte is an 8-bit binary number. So if you have 8 bits, shove them together, and you get to call it a byte. And now you know where all that comes from. So here's like, I don't know, 101101 base 2. This is a 6-bit number, yeah? Whee. And then here's a byte, 10110011. Why not? Base 2. This is 1 byte of information encoded in binary. And yeah, just understand right now that this is 2 and this is 10, which means numbers in different bases are not the same when they look the same. So this is like, I don't know, 1010 in decimal. That's not equal to, right? not equal to 1010 in binary. I'll show you how to convert this, but this is going to be a much smaller number, okay, if you follow the pattern. Any questions about binary so far? We doing okay? All right. And then people think that we use decimal because we have 10 fingers. So maybe if we lived in the Simpsons world, we'd all be using base 8. All right. So let me show you how to convert. All right. Let's convert a binary number to a decimal number, because who knows what this is until we make it in our number system that we understand. Okay. And so the trick to going that way, to go from binary to decimal, is to write out the expansion of this number using exponents and cool stuff like that. So let me show you how to do that for just decimal numbers all over again, because that'll help us understand how to break down a binary number. Okay, so remember, if you have 1,234, we learned this in like elementary school or middle school, right? That is the same as 1,000 plus 200 plus 30 plus 4, right? And then you can break that down further once we learn about exponents. That's 1 times 10 to the third plus 2 times 10 squared plus 3 times 10 to the first plus 4 times 10 to the 0. Yeah? So that is how you break down a decimal number into its individual places. And look at where the base appears. That's the thing being taken to a power. Interesting. And so it turns out that this pattern works exactly the same for binary. It's just we're not using base 10, we're using base 2. So that will tell us what this number really is. All right? What is 10010 in binary? Well, let's write it out. That's going to be 0 times 2 to the 0. Usually you start on the right, that's that digit. Then 1 times 2 to the 1, right? Plus 1 times 2 to the 1 plus 0 times 2 squared plus 0 times 2 cubed. It's always going to either be 1 or 0, which is interesting. Plus 1 times 2 to the 4th, right? And so that's, if you just do this math, that's the decimal number that this binary number was encoding. And so simplify it, convert it to decimal. So it looks like 10010 in binary was the decimal number 18. Okay, if you just fill out that expansion with the base you're using, then you can convert to decimal. Any questions about how that's working? Yes? Yeah, it's always like that. So this is the 10 to the zeros place. This is the 10 to the ones place. So it all works similarly. This is the 2 to the zeros place. This is the 2 to the ones place. It always starts at 0 though. Yeah. Any other questions? All right. So, okay, you try. Take a minute, go get into your peer instruction groups, introduce yourselves, and try to expand this number. What is this binary number in decimal? Take like 2 minutes to try it out. You don't have to write it down on anything but your paper. Hopefully you're getting it. Yell at me if you have questions. All right, that's my timer. Hopefully that was enough to get started at least. Let's talk about it. So this is 1 times 2 to the 0 plus 1 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 cubed, right? Mm-hmm. All the ones, starting at 2 to the 0 though, the ones place. It's always the ones place no matter the base. 1 times 2 to the 1 plus 1 times 2 squared plus 1 times 2 cubed. And so that, you're going to get really good, if you aren't already, at powers of 2. So that's 8, 2, 4, 8, plus 4, plus 2, plus 1 equals, drum roll, that's 15 in decimal. Did we all get that? Are there any questions about how we got this? Yeah? Not too bad. Okay, so that's the easy way, going from binary or any other base to decimal, because we know how to do math in decimal. The other way is harder. If you want to go from decimal to a binary number, like what is 123 in binary, that way is unfortunately more difficult. So let me show you the algorithm here. It's going to be a fun one. So what you have to do to convert from decimal to binary is repeatedly take remainders and divide and throw away remainders. With an example, this will make more sense. But remainders are key, okay? That's the idea. So essentially, we want to extract the digits from a number, not the individual digits in decimal, not like the 1, the 2, and the 3, but the binary digits of this number. Okay, so let's talk about how to mathematically extract just the normal regular decimal digits. How do I get like 3 out of 123 and the 2 and the 1 by itself? How can I do that? Let me show you, okay? So if you want to extract the digits of a decimal number, you can get the rightmost one, you can get that 3 out of there by dividing by 10, okay? And then looking at the remainder, because here's 123. If I divide by 10, it gives me 12 remainder 3. Do you remember that kind of math? That is the 3. You see that? That's the rightmost digit of 123. That's how we can get that. All right? Then, to get the rest, I can follow that same pattern. If only I could just convert 123 to 12, because then I could do the same thing. Divide by 10, drop the remainder. So let's do that, okay? How can I convert 123 to 12? Well, just divide by 10 again and take this. Take the quotient, don't take the remainder, right? Throw it away. So that's how you can do that. That's how you can get both of these. And then you keep following this pattern. Once you hit 0, you're done. So let me show you this, okay? And there is a expression in most programming languages that divides and gets a remainder. So it's the percent sign. So if I use a percent sign, that means like this, 123, get the remainder after dividing by 10. That gives me the 3. That's this operator. It is called modulus, if you care. It's called the modulus operator. It gets the remainder after dividing. So it kind of looks like division, but it's slightly different, right? Division and throw away the quotient, only give me the remainder. So I'm going to use this notation, all right? So let me show you how to extract the digits of a decimal number all over again. So first I start by extracting that 3 by dividing by 10 and taking the remainder. So that is the modulus operation, which I will lovingly call mod. Okay, so 123 mod 10 is 3. That gets me a digit, okay? And then I want to convert this to 12 so that I can do the same process, get the rightmost digit. That's 123. Divide by 10 and throw away the remainder. That is just 12, okay? That's how I do that. And now I have 12 to work with. Cool. If I can just extract the digits of that, then I will be done. So then I can use 12 mod 10. That gives me, it goes in once, right, with 2 left over. There's my 2. And let's shift away that 2 so that I just have the 1 left. So I can extract all of its digits, which is just that last one. So 12 divide by 10, drop the remainder. That's 1. 1 mod 10. It doesn't go in at all with 1 left over. 1 divide by 10, throw away remainder, 0. Okay, and that's, once we reach 0 in this algorithm, we know we're done. And every time we took a modulus, we extracted a digit, and we did it in opposite order, so reverse order. So that's how you get rid of, or extract all of the digits of a decimal number. Does that process make sense at all? It's a weird one, but that's the trick. And remember, when you're dividing, you forget the remainder. Throw away remainder. Because it just so happens that, oh man, here's the base again. If I change that to 2, I will extract the binary digits, the bits of a decimal number. Yes?
For the second row,
This? What's wrong with this? I'm throwing away the remainder. It's this kind of old school, when we first learned about division kind of math. It was 12 remainder 3, right? So I'm throwing away the remainder for this kind of division. Some people call this integer division. Some people will draw 2 slashes to make sure that it's clear. But yeah, it's just division with throwing away the remainder. Okay? Good question, though. It'll take some time to get used to. Any other questions about this process? All right, so let me show you that this works for binary. If only I could extract the rightmost bit, then shift away that bit. I can just change these to 2s, and it will work. Okay, so let me show you. So repeatedly extract the rightmost digit in binary by using mod 2, getting the remainder after dividing by 2. And then we shift away that bit that we extracted by using division by 2 and dropping the remainders. It's integer division, we say. Okay. So let me show you how to convert 8, the decimal 8, to binary. So I'm going to do this process. What's 8 mod 2? That extracts the rightmost bit. And this is an even number, so there is no remainder. And then I want to shift away. This is the rightmost digit in binary of 8. I want to shift away that 0 and get a smaller number that if I convert that to binary, I will build up all the digits. Okay, so then I do 8 integer divide by 2. Dropping any remainders. That gives me 4. And then I have 4. If I just convert that to binary, getting the rightmost bits all over and over again and shifting them away, then I will have the actual final binary number. I'll get all the bits. So 4 mod 2. That's again even, so remainder is 0. 4 integer divide by 2. That's 2. 2, let's convert 2 to binary. What's its rightmost digit, rightmost bit? 2 mod 2, again it's even, so 0. Let's shift away that 0. 2 integer divide by 2, 1. 1 mod 2, that's 1. And then, how do I know when I'm done? I needed to do 1 integer divide by 2, shift away that 1. That equals 0, and then I'm done. Okay? So every time I took a modulus, I found the remainder, I found a bit. And you read it off backwards. So 1, 0, 0, 0 is 8. Isn't that nice? So it equals 1, 0, 0, 0. Base 2. Okay, and that's the answer. Any questions about that? It is the right answer, right? That's the 1's place, the 2's place, the 4's place, the 8's place. We got one of those. All right. So with this in mind, I can highlight that. I can maybe copy all this so that you can see the process. Because now I want you to try, right? Please convert decimal 25 to binary. take a few minutes to try this one out. I'll give you 3 minutes this time, okay? Convert 25 to binary. Feel free to break out a calculator. And once you get an answer, you can check it, right? Because you know how to go the other way. Determining the remainder of 1, 2 is always odd versus even. It's odd, it's 1, it's even, Try checking your answer if you're already finished. That's the easy way, right? Going from binary back to decimal. All right. Did we get an answer? Not sure if it's right, but did we get one answer maybe? An answer. Well, let's do it. Let's do it together. So, start with 25. I want to extract the rightmost bit out of 25. So I'm going to do mod 2. Is it odd or even? It's finally odd, so the answer is 1. There's 1 left over when you divide by 2. And then I want to shift away that 1 bit out of 25 so that I can make a smaller number. If I convert that to binary, then I'll have the whole answer. Okay? 25, divide by 2 using integer division, dropping remainders. That is, what, 12 and a half, so just 12. And then I just convert 12 to binary using the same process. Extract the rightmost bit of 12, 12 mod 2. That's even, so it's a 0. And then shift away that 0 out of 12. So divide it by 2. Integer division. So that's 6. 6 mod 2 equals 0 because it's even. Shift away the 0 out of the 6. 6 divided by 2, that's 3. 3 mod 2, that's 1. There's 1 left over. 3 divided by 2, just 1 because we're dropping remainders. 1 mod 2, that's 1 because it goes in 0 times with 1 left over. And then 1 divided by 2 is 0. And that's how we know we're done. So if we read off every time we took a modulus operation, we read everything off backwards. Remember that it's backwards. Then we have an answer. 1, 1, 0, 0, 1. Okay, base 2, and that's apparently the answer. Now we can check this pretty quickly, right? Because this is the 1's place, this is the 2's place, this is the 4's, the 8's, the 16's place. That's 16 plus 8 plus 1, which is 24 plus 1, 5. 25. Yep. So that is in fact the answer. Whee. Any questions about how I got this? Did we get that? That's the hard way. So pat yourself on the back if you're understanding this at all right now. Definitely come back to it later if you're not, and ask me questions. All right. So, are we good to move on? Okay. So that's base conversion. It's very fun. Now let's talk about let me just show you an example of adding binary numbers, because why not? Watch what has to happen. 1 plus 1, that's 2, but in binary, 2 is 1, 0, so you have to carry 1, 0. Isn't that cute? And now it's 1 plus 0 plus 1, again, 2, 1, 0. You got to carry again. Now we have 1 plus 1 plus 1, that's 3 in binary. That's 1, 1, so we carry and also add a 1 in our current place. Yay. And then finally, 1 plus 1 plus 1, that's 3 again, 1, 1 in binary. And so the final answer is 1, 1, 1, 0, 0, base 2. Okay? And this is all equivalent. If you convert all these to decimal, that's apparently 8 plus 4 plus 1, that's 13. That's plus 15. We know that one now. And this is apparently 28, which should be correct. 16 plus 8 plus 4. 24, yeah. That should do it. Okay? So that's just a quick little fun thing about adding binary numbers. It's all the same, you just have to carry sooner. Yeah? Okay, so I taught you all this, but for what? Why in the world should you care? Let me show you how all this stuff in these slides link together. So, and then we'll start a new set of slides. A circuit to add numbers. Oh man, oh man. So how in the world does our computer use binary to do real work? How does it use these logic gates, these operations? Let me show you something simple. Let me show you addition. Let me show you how a computer would do addition. Okay, it's all in binary, of course. So that's why I showed you that. Oh man, what if you look at the XOR operation? Let's go back to that. Exclusive or all these things. Think of them in terms of 1s and 0s now, though. But if you squint at this and write it in terms of 1s and 0s, where true is 1 and false is 0, XOR, exclusive OR, is doing 1-bit addition, actually. Isn't it? Because 1 plus 1, well, that's 1, 0. Just we're pretending we only have 1 bit to work with, so it's 0. 1 plus 0 is 1. 0 plus 1 is 1. And 0 plus 0 is 0. This is exclusive OR, isn't it? When they're different, it's 1. When they're the same, it's 0. That's how you can legitimately add numbers in a computer, okay? Then you have to worry about, okay, we have to put a bunch of XORs together to add a bunch of bits. And so you got a bunch of those. This is what exclusive OR looks like in a circuit diagram. But here it is. You just, okay, here's the sum of those 2 bits. And then also, you might need to carry. And so you need to carry if they're both 1, right? So A and B, if that's true, then you carry. And so you can chain a bunch of these adders, these 1-bit adders together, and make an addition circuit. I'm not going to test you on this, but hopefully you can see that this is useful, okay? Any questions about this slide, this idea? It all comes together in the end. And also, any questions about these set of slides in general before I switch to a completely different one? All right, so this is fun math stuff. So that is logic circuits and binary. Let's now talk about privacy and encryption. Also fun, just slightly less math, okay? More words. So let's talk about first privacy on the internet in this digital age in which we live. So there's a lot of different stuff. Like if you think about privacy back in the day, there was a lot less that could go wrong, right? You have like houses, you're sending mail to each other, physical mail. You don't have like people connected electronically. How did all of these laws evolve? How does this work nowadays? Okay, so let's first talk about, I guess, U.S. specific stuff. We have the Fourth Amendment, right, which prohibits unreasonable searches and seizures. So if you want to like break down someone's door, look in their house for stuff, you need a warrant and you need probable cause. That's nice. But that's like your house, right? That's your physical stuff that you own in your place. What does this mean on the internet? The internet is not physical, right? It's a different kind of place. Are you ever, should you be guaranteed privacy even? It's a public space, maybe, the internet, we could say. It's just a bunch of wires connected. So it's definitely not our house. So back in the day, the Supreme Court first ruled about how this works for telephones. So if you wanted to tap a phone, the Supreme Court originally thought that you didn't need a warrant to do that because it was just phone lines, just wires sticking out places. Didn't have to go in anybody's house to tap a phone. And they thought that a conversation was not a tangible object as well. So that was the first time people's rights got a little messed up thanks to electronics. But luckily, at least for wiretapping, they changed the way that they thought in the 60s. And so now they think you do need a warrant to tap a phone. So that's nice. What does this mean on the internet, though? Think about it that way. There's things that could go wrong. There's a lot of things that are different. The internet is not a phone. All right, so I think just this little subsection, I have a bunch of little examples for us, and I want it to get you thinking about, do we deserve privacy on the internet? What does it mean to have privacy on the internet? Okay, so here's a fun example from the textbook. Target, like every company does, they like to data mine. Okay, so if you buy stuff, they want to track your purchases and maybe send you targeted ads to make sure that like you buy more stuff from them. They want to keep you coming back, right? So they noticed that pregnant women would buy certain products, right, at certain stages of their pregnancy, and they used that to give ads to those women, right? So they took that data, they mined it, which is just a fancy term for pattern finding. They look for patterns in data, pattern finding. Okay, that's what data mining really means. Just looking for patterns, seeing what's up. And so they took all that data from the purchase histories of pregnant women, and then they went and sent targeted ads to them and coupons. And I love that pun because it's Target. And then we can ask the question, does this infringe on their privacy? Should Target have not been trying to do this, right? And so we could ask our boys about this and see what they might have said. So Kant would ask, hey, should everyone always be looking into the purchase histories of their of the people that they are like providing a service to? And I think Kant would probably say no. Most likely, he's for individual rights. He's like, I don't want to spy on my neighbor. I like privacy. I think Kant would be pro-privacy most of the time. Okay, I think he would answer no to this question, but you could think of a good enough argument to make him say yes. It's just a way of thinking about something, right? These different ethical theories. And then the utilitarians would think, okay, is there utility in doing this? So again, you might be like, oh no, the privacy issues outweigh the gains from these, like the savings that these women would get by receiving these ads and these coupons. Or you're like, oh yeah, they're saving money. The utilitarians might like that. That might outweigh the privacy issues with this. Okay? So that was a fun news story. I think this happened back in the early 2010s, so like 2013 or something like that. I think that's when this came out. Don't quote me on it, though. Do we remember hearing about this? It's an interesting little thing. So should you be able to do this as a company? Are the purchase histories of your customers private? All right. So that's fun. And also they could figure out whether or not someone is pregnant. Like they didn't ask the women, are you pregnant? They just noticed that they would buy these certain things. Okay, and they made inferences about that. All right, so that's the first topic. Let's talk about ad blockers. All right, so I encourage you to use one. This is called uBlock. I installed that on all my little devices. The internet looks much better with an ad blocker, but let's talk about it from an ethical point of view. So it is not illegal to block ads on a website. Let me just say that first of all. But it is technically illegal to block ad blocker detectors on websites, which is fun to think about. The reason for that is because you are tampering with the website's access control, and that is something that they should be allowed to do, right? Facebook doesn't want you to be able to log into your friend's account, so they use passwords. And so technically ad blocker detectors on a website is access control, and websites are allowed to control that access. Okay? So, still, is that okay? We can ask our boys. These are great little ethical questions, and I want you to be thinking about them in your minds, okay? Because this all goes back to privacy on the internet, right? Do we have any rights at all? So let's think about Kant right now. He would ask, should we always use an ad blocker? Or if you flip that around, should we always be not using an ad blocker, which means should we always be looking at the ads that we see on a website? Should we always be clicking on them because that's how the websites make money? Is that something that we should always do? Should we always buy the products that are advertised to us on the internet? I think any reasonable person would say no. And so Kant would be pro ad blockers, wouldn't he? Interesting. Please shout out if you have any comments on this. These are fun little topics for me, at least. And then, again, the utilitarians would ask, what are the benefits of doing this kind of thing, of blocking ads on the internet, of not doing that? Okay? So, again, there's pros and cons. So maybe a pro for ad blockers is there's more real content that you see. When you have a bunch of ads on a page, you can't really, it like blocks the article that you're reading. You have to scroll down even farther. More real content. It just kind of makes it ugly. Okay, there's a bunch of little boxes everywhere. With an ad blocker, those all go away. So maybe you're going to get more use out of your time if you block ads. So that's one side of the coin. And then on the flip side, a con against ad blockers would be something like the websites that are showing you ads, hopefully they're trying their best to not do it obtrusively, they are making money based on showing those ads to people. And so if the ad is not downloaded because your ad blocker is blocking it, then they are making no money. And there's zero chance when you're blocking the ads for somebody to accidentally click on it or purposefully click on it, and that makes them even more money, okay? So the website might go out of business if it's a small one, okay? So those are the pros and cons of ad blockers. Again, this has to do with privacy, doesn't it? Any thoughts, questions about this? Just a bunch of little examples to get our brain working, yeah?
So it's like tampering with access control. Like what exactly is that using someone else's credentials? I think it's more like say if you're going to like a newspaper website and they want you to basically only view it with a subscription or only allow the person to trial it and they want you to access it.
That's a good example, yeah. It's something like, okay, they're making money based on them showing you ads, and that's how they stay in business. And that is technically controlling access to copyrighted content if you're writing a copyrighted newspaper, right? Anything that you print is copyrighted. So that is their justification. Yeah, it's a good question, though. Maybe this won't hold up in like court much longer. Who knows? It does seem like a weird little argument, a weaker one. But it is one, nonetheless, that is accepted. Yeah, so this is a great little conversation. Let's continue on my last example here for this little subsection. Let's talk about Google Street View. I took this screenshot a little under a year ago. I don't think much has changed. But in blue is all the little tiny streets that are mapped and photographed by Google Street View. The little car that goes around, everybody waves at it. And it maps the streets. And so you can see like, okay, this is what this storefront looks like. That's Google Street View, right? Let's talk about the Germans. So not everyone loves Google Street View. Not every culture, even a European culture, has the same thoughts on privacy. Okay, so Google Street View in pretty much all of Europe is everywhere, like every single street in the UK, in France, Denmark, Poland, all of those places is mapped. They had the little car go drive around and take little pictures, except for Germany. Only in the bigger cities do they have anything at all. So that points to a cultural difference that translated into a legal difference. Okay, so Germans are a lot more mindful of their privacy, it seems, and they have laws that reflect that. Okay, so they don't allow people's houses, for example, to be photographed by Google Street View. That would be, to the Germans, an infringement on their privacy. Okay, does that make sense? Weird. Like, I want to know what this address is, like the front of this house looks like, so that I know when I'm there. But that is U.S. culture. That is not speaking for everyone. Okay? And so you can ask the question like, okay, what are the pros and cons of this? Think about this as a utilitarian. The Germans made one, they took one side over another. Okay? Isn't that cool? Interesting? Any questions about this before I get into a different topic? So this is privacy. So it comes in different forms on the internet. I've showed you that. And also, some people hold different views. All right. So next, I want to talk about encryption, because that's one way to maintain privacy on the internet. And let's talk about that. All right. So let me first define what encryption means. Encryption is just, the process of encoding information. That's the fancy definition. It's making information jumbled in a way that only you and the person you're trying to send the data to can understand it, right? Only the people that a message is intended for, that's like the technical term, you're trying to send a message to somebody. Only the people that the message is intended for are able to decode the information. So encryption is encoding, and then it also has to do with decoding it again. Only certain people are should be able to decode a message, okay? And so this is used everywhere. Even on our class website, I use HTTPS, right? So it really is everywhere. Security and commerce are the biggest things, the biggest uses of encryption on the internet right now. Okay, so that's just making sure that when you go to a website, maybe you have to log in. Encryption ensures that nobody saw your password being transferred to the website as you were logging in, right? It's ensuring that the page that is sent to you by the server, like your, your Facebook welcome page with all your friends' information, that's only being visible, that's only visible to you on the other end of the pipes that make the internet, right? That's what encryption is ensuring. Also, like when you're making a purchase, it's making sure that your credit card number, it's just like a password, right? It's only getting sent to like Amazon if you're buying something on Amazon. Even though, like, the ones and zeros that make up your credit card information, all the data that's being sent to Amazon or wherever you're buying stuff from, those are traveling through like Comcast, back ends of the internet. They don't even get to see it. They have no way to decrypt it, or it would take them a very long time to decrypt it, more than like thousands of years, I would say, okay? Unless you have a very, very powerful supercomputer. That is essentially encryption in a nutshell. Any questions about these definitions, what they mean? So I'm going to show you some examples of encryption now. All right. So first example is very simple, very easy to break, but it at least gets the conversation started. Let's talk about something that was made in the Roman times, so the Caesar cipher, aka ROT13, and the ROT part stands for rotate, okay? So it rotates every letter of the alphabet, and that becomes jumbled enough to be encrypted, okay? This means rotate by 13. And so if you have a secret message, like hello, you're trying to send to somebody, then what you do for the Caesar cipher, or ROT13, is you shift every letter of the alphabet 13 letters over, and you wrap around once you get past Z, you go back to A. So essentially you're doing A plus 13, and apparently that gives you N, okay? That A becomes N in the Caesar cipher. So you just replace every A with the letter N, right? And so you'll end up with a jumbled mess and hope that it's encrypted, right? So if you were to translate hello, you'd make it, okay, H becomes U, E becomes R, L becomes Y, and B becomes, O becomes B because you wrap around. Again, it's 13. And so that translates hello into Urib, apparently. And a nice thing about the Caesar cipher is there are exactly 26 characters of the alphabet. And so if you rotate by 13 and then you rotate by 13 again, you go back to where you started. And so this is its own inverse. You just redo the encryption and you end up with hello again. So this would be the message you send to somebody, I guess back in the Roman times, that was good enough and encrypted, okay? Of course, you can attack this, like certain characters are more common than others, so if you send a very long message, it's possible to break this encryption quite easily. But it's a nice, simple example. That is the Caesar cipher. Any questions, thoughts about this before I talk about a modern-day encryption algorithm? All right, so let's talk about advanced encryption, stuff that you cannot break without like a large government's worth of supercomputers. So let's talk about something called RSA, okay? It's actually, this acronym stands for the three people's last names who invented it. I don't remember how to pronounce them all, so you can look it up on Wikipedia. It is a very, very interesting encryption method, okay? The idea for RSA, for encryption that exists these days, is there's a concept of a key, okay? There's a key when you're signing something. So we have a message, we're trying to send somebody this cloud, and we sign it, we say, with our key. And then that is going to encrypt this information. That's what we send to somebody, okay? It's actually our key plus the other person's key. So that's an encrypted message in the idea, okay? So how do I want to explain this? There are two different keys in RSA. There is what's called a public key and a private key, okay? And the key that you're using when you sign a message is the public key of the person you're trying to send it to, okay? And they can decode it with their private key. Because they come hand in hand, that allows for you to decode information. I'll give you an example on the next slide. It'll make more sense. But it's very cool. It's very mathematical. But there's something that you give out to people. You give your public key to everyone who asks for it. And then you save away your private key. That's like the password for encryption, for decryption even. Okay? So one thing you share with people and one thing you keep for yourself, and that allows you to have very, very strong encryption over information. It was invented back in the 70s, and if you just make big enough keys, then it is uncrackable, okay? For all intents and purposes. It's so secure that it's still used today, which is wonderful. And the reason it works so well, the reason it's effectively unbreakable, is because it's really, really hard. It's based on mathematics, a bunch of number crunching. It works because it's really hard to factor numbers, okay? That is, like, these are very large numbers that only have two factors that are hard to find, okay? And that's how RSA works in a nutshell. But let me draw you a better example of what's going on here. So here is you. Somebody's trying to send you something. And so here's the sender of some private information. And so you have a private key. So does the other person. You have a private key that you keep just for yourself. Okay? So here is you saving your private key. And then the sender wants to send you something, so you give them your public key. Anybody can ask for it. Public key. You put that on the internet. So you give them your public key, and then they take their message and they sign it with your public key. Boop, boop. And so there's the encrypted message. And the way the encryption works is you can use the private key to unwrap this message and decode. Okay? Again, this is probably way too vague without an example still, but let me give you one now. Okay, any questions before I give you that example? Does the idea make sense? Public key, private key, yeah.
Like on those websites, there's like that like lock symbol. Does that like mean it's like encrypted by using the RSA?
Yes. So this is HTTPS, lock symbol, connection is secure, more information. Yay. So yeah, it's essentially, it's using a fancy encryption scheme. It's somebody has signed something, like somebody that we trust, some company that we trust to say that the internet is okay, these websites are okay. I signed up for that, and they tell you that my website is all right. So there is I guess it's not, it's called AES. That's the encryption scheme. It's very similar to RSA, though. All of these modern day ones are. But yes, it is encryption going on when you connect securely to an HTTPS : or HTTPS : website. Great comment there. Any questions about this? And you can view this certificate. It's like, okay, here is the person saying that this website is all right. We trust them. Oh, nice. They actually did use RSA. So there is a public key. It is using RSA, and this is how big the key is. Super large. Very nice. And then once you exchange keys and have a connection, then you use something called AES. That's where I got, oops, a bit backwards. Is that still happy? There we go. So yeah, great question. And all the websites, even Canvas, secure connection, more information. We're connected using, okay, yeah. This one has RSA baked into it at the beginning. So people are using this encryption scheme. It's wonderful. Dun, dun, dun. So let me give you an example of it. All right. So this also uses modular arithmetic. So good thing I taught you the % symbol that gets the remainder of things. So let's have these numbers as our example. Okay, these are parts of a public key and a private key. So a public key is two numbers. It is a number N and a number E. Okay, so N is this number and E is this number. Just in our example. They're supposed to be giant though. And then a private key is just a single number. We'll call it D. Okay, and the way we got at these numbers is we used a prime number to generate them. Okay, it's all about primes at the end of the day. And D and E are modular multiplicative inverses. You don't have to memorize any of this. But what it means is if you have some message that is a number that you're trying to send to somebody, because everything is just a bunch of ones and zeros, it's always a number. If you take that to the power of E or D, and then you take it to the power of the other one, D to the E or E to the D, then you get back that same message. We say mod N. Okay? So you have to do some modulus by this number to get back that same message. But essentially, you're going to get back M all over again. That's how you encrypt and decrypt. Okay? And you're allowed to send any message you want. That is a number between 0 and n-1. So usually n is much larger. And you kind of skip 0 and 1 because weird math happens there. We don't need to talk about that. But if you have a message and you want to encrypt it and send it to somebody, you calculate m to the power of e and take that mod n. Okay, and that's your encrypted message. Usually we call that cipher text. Again, you don't have to memorize these terms. But let's pretend that we're sending a message of the number 42 to somebody. Okay? And we get their public key. They gave that to us. So we're going to send m to the power of e mod n, because we got both of those numbers from their public key. Okay? So let's calculate m to the power of e mod n. So let's do here in Python. You'll learn this eventually. So 42 is the message to the power of e, which is 17. And so it's a giant number, right? And then back down to something nice, we do mod n, so mod 3233. Yay, so apparently the encrypted message, the cipher text is 2557. And so that's what you send to the person. And they can magically, using their private key, get back to 42. Okay, to decrypt a message, you do C to the power, the message, the cipher text to the power of your private key, C to the D, mod n again. Okay? So let's do that. 2557 to the power of D, which is 413. Ooh, that's a big number. But then we do, we get the remainder, mod 3233, mod n. And what do you know, that's 42. This all comes down to be a tiny number, 42, and that's encryption in a nutshell. Whee. So that was the M all over again. Isn't that cute? So if you take CSCI 26, I'll explain this in a lot more detail, but hopefully this was enough to get us started. Any questions about RSA? It's all over the internet. It's very powerful. All right. I guess while there's still time, let's have a quick little debate, because I think that would be fun. I've got you thinking about all this stuff. Let's ask the question, is it ethical to use encryption to send messages? Is that okay? Let us debate first, and then we'll ask Kant and Mill at the same time, okay? So here is our debate. Let me split you up into groups, as usual. So let's do this. Go to the written nice page, because you're going to be writing down your arguments. Let me clear it out. Boop. And then using this room map and the group number that you get out of it, right? Please understand what group number you're in, because I'm going to split you into even groups and odd groups. So if you are an even numbered group or an odd numbered group, you're going to think different things, okay? So here's the question. Is it ethical to use encryption to send messages to somebody else that nobody else can see or decrypt other than those two parties that are involved? And if you're an even group, I'm going to say yes, you are for encryption. So write some arguments in terms of that. And if you're an odd numbered group, you're against encryption. Okay? So write down, try to get to 2 arguments in support of your stance, and then we'll talk about our thoughts. Okay? So let's have a little mini debate, and please write down the arguments that you come up with as a group. Is it okay? Is it ethical to send messages privately on the internet? Eventually, I'm going to require a recording, but for this one, I said a screenshot was okay in the directions. Yeah, so I said both. I said, I want you to record if you can, but I said for this one, you can just do a screenshot if you're unable to record. But by next time, you can be ready and able to record. Okay. All right, thank you. Yes.
How do we check our groups again?
Oh, there's another tab on that page. Are you already on the written nice page? So go to the written nice page, and then there's this room map at the bottom there. Oh, no, you're good. Yeah. That's how you determine your. Try to not look at the other group's responses. Come up with your own. It's a little low. You having good thoughts? Take a minute and a half more to write something. All right, 30 more seconds and then we'll talk. All right, let's come back together and discuss some of these arguments. Let's see which ones we like the best. And then we'll talk together about what we think Kant and Mill might say to all of this. So let's go here. Dun, dun, dun. So the even numbers are for encryption, and the odd numbers are against encryption. So let's take a look here. Ooh, nice job using Kant, group 6. So everyone is entitled, this is an argument for, everyone is entitled to privacy, only with consent. Others should listen to our messages. Okay, yeah, and that would definitely be something Kant would be for, and we'll talk about that in just a second. He's for individual rights and privacy. Let's look for an odd-numbered group. Go to the bottom, maybe. All right, so an argument against, if we can't monitor conversations, then we do not know about any threats to public safety. Yeah, that's why every government has like a signals intelligence group that is important for safety, especially back in the day. And the elimination of private thought would bring unity. Is that a good thing or bad thing? I can interpret that two ways. Nice. I like it though. Yes. These are great arguments. Let's look at two more. It's unethical to use encryption because the amount of privacy could lead to harmful events. Yes, it's usually about peacekeeping, things like that. Those are the strong arguments against encryption. That's what's going on there. What about another 4? Oh, nice. Using utilitarianism, group 20. Has many uses. Private conversation. Yeah, if you want to have a private conversation in real life, it's easy, and maybe you should be allowed to do that on the internet as well. Encryption allows you to do that. So, great job, everybody. Read these from the other groups as well, if you'd like. But I'd like to move on just a little bit more to talk to have enough time to talk about your next essay. Okay? These are great thoughts. I especially enjoy some of these colorful conversations. Anarchist dream, I enjoy that. All right, so let's think about, we already talked about this a little bit, what would our boys say about these things? What would Kant ask? What would he respond with? What would Mill say about all this? I think Kant, he is always for individual rights. Should we always do something or not? Should we use people as a means to an end? Of course not. So Kant is probably someone who would say private information should be kept private, even on the internet. And so he'd be for encryption. Even if, like, our enemies can use it too, that's fine. Everyone should be allowed to have private conversations with each other, even encrypted ones. Okay? And then Mill, I think you could, it's usually easier from the utilitarian's point of view. Kant is a bit more focused on certain things. From a utilitarian point of view, you can usually pick both sides, and depending on how you argue it, you could talk about either way. So you break it down into the pros and cons, right? So Mill might be for privacy, like privacy is a good thing, therefore encryption is a good thing, right? Or that's like a pro. A con would be you want to intercept transmissions if, like, between bad people, if you define bad in a certain way. So it might make it harder to protect people. Protect people from harm. If you didn't have encryption, it would be easier to protect people, maybe. You could say that. Okay? So those are some pros and cons, and I'm sure we've written a few more, and you can think of a few more as well. But yeah, any questions about this? Hopefully that was fun. I like your long responses. It seemed to be like you guys are having fun too. So awesome. Are you ready to move on to one last topic before I talk about your next essay? Because you got one due this week, right? So let's talk about three people, three ideas, I guess. Mostly people, though. So let's first talk about Chelsea Manning. These should be some names that you might remember, right? So back in 2010, Chelsea Manning gave WikiLeaks, remember them, a bunch of classified information, right? Either like almost 1 million different documents. So most of it was classified, some of it was unclassified but sensitive, right? These were all things being sent between the military and just diplomats in the US. And that was insane, right? Can you think about how hard that would be to do for one person to do back in the day when it was all physical documents? But no, this was a bit larger because it's all virtual nowadays. Crazy, huh? So a lot of things she leaked. And because of that, she was sentenced to 35 years in prison, okay, for doing this, even though she thought it was the right thing to do, right? So that sentence was eventually commuted by President Obama back when he was still in office, and I think she's out now, as far as I can tell, as far as I remember. So that is the gist of it, and we want to think about, does the value of informing the public, because the things that she leaked, I can't remember exactly what, but they did not paint a good picture of the U.S., what they were doing. I think it was a lot of Afghanistan kind of stuff, showing that like civilians were being harmed and that was not being like shown to the like people. That was being kept under wraps, things like that. So she thought that she had a duty to inform the public, right, of these horrible things that were going on. And then it was illegal for her to do what she did because all of these confidentiality laws. These were a lot of classified documents, right, or sensitive documents. And so you have this weighing to do if you're a utilitarian, like should I do this? Should I not do this kind of thing? Because on one hand, like the reason they didn't like this, the reason people were really mad at WikiLeaks is because they didn't like block out people's names or anything like that. And so they thought that those people might be like targets because of it. So on one side, you have the idea that confidentiality protects people. Maybe it would have been better if WikiLeaks blacked out everybody's name in all these millions of documents. But on the flip side, you have the idea of if you have this information in the open, you could give people more knowledge, right? And knowledge is power. So you could give more information to people who are maybe ready to vote in a future election and want to change the way that, like back in the day, the war in Afghanistan was going, things like that. More information for voters and activists to have their voices heard. And so there are two sides to every coin. And this was Chelsea Manning's story. Again, a very quick version of it all. Any questions about that? All right. So I want to make sure we have enough time to talk about all this. Let me just go very quickly through the Panama Papers. A bunch of documents were taken from a law firm in Panama, and there's a lot of financial stuff. Foreigners are making offshore companies to invest a lot of money, and a lot of people thought that that money was corrupt. So that was a big leak. But a lot of the time people weren't doing technically illegal things. But again, it was a huge, huge leak. And feel free to look more about that on Wikipedia. I want to have enough time, though, to talk about Edward Snowden. Okay? Snowden was a contractor back in the day for the NSA. He leaked a bunch of documents, just like Chelsea Manning, a little bit later in 2013, showing how the NSA was spying on U.S. citizens or putting back doors in popular things. Again, a lot of classified information that he shared. And he brought to light the fact that the NSA was capturing a lot of information on the internet when they were not legally even allowed to do it. Okay, so that was a big deal. And he was indicted for espionage because he was giving away classified information. And he right now is living in Russia with his wife because if he ever leaves and goes to a friendly country with the U.S., he will be arrested and prosecuted. Okay? Because he still broke the law. Question? Because he gave that information out to the people. He showed that, okay, he leaked all these documents showing that the NSA was doing these bad things. And leaking classified documents is unfortunately illegal. Yeah. So there's a lot to talk about there and to unpack, but I think that's a fun little topic. And while we have 2 minutes left, I want to show you your next essay where you will learn more about him. Okay? So you have a new essay coming out because you have an essay being due. And so here's a 500-word essay. In the last 2 minutes of class, let me explain it. Here's your prompt. Tell me, was it right for Snowden to blow the whistle like he did? He's a whistleblower, right? On the NSA. Do we have a right to privacy on a public utility like the internet? Because that's what it is. Everybody can use it. We're not so worried about PG&E, right? They're monitoring exactly how much power we're using, and nobody like goes and pickets outside of PG&E's office. What's different? Tell me. And this essay will be 500 words to that prompt, okay? So I want you to remember to make a good argument, mention both sides, maybe bash down somebody's, one of the sides and prop up the other, right? You don't have to talk about Kantianism or utilitarianism, but you can if you want to. And then finally, this is your first essay with a citation requirement. You have to cite at least one source when you're writing this essay, okay? So here's your prompt. Here are your guidelines. Go and research Edward Snowden a little bit more, okay? And write a good 500-word essay. And that, my friends, is all I have for you. This is going to be due week 6, so that's the 15th. That'll be the Tuesday of week 6, okay? Publish.